Apart from Dr. Davison's formal education and accreditations, he is a man with a wealth of experience in research and development leadership. Some of his experiences include the head of Reactor Control Design Group at Atomic Energy of Canada. Also, he was the Director of Research for Fluid Power and the General Engineering Manager with Philip Cables. Dr. Davison served as the Industrial Technical Advisor for 17 years with the National Research Council of Canada. While working here, he actively contributed to the development of such companies such as RIM, OpenText, DALSA, and Orchid International, to name a few. He served as a university professor for 11 years and taught various engineering disciplines. Dr. Davison also had the opportunity to be involved in the development of the Avro Arrow and worked on various aspects of this historic jet. Dr. Davison is very highly regarded amongst his colleagues. He has worked and studied for years in the area of motor technology and is now considered one of the world's experts in the area of harmonic drive motor generator technology. Simply put, Dr. Davison is a highly intelligent man with a vast amount of experience. He has the know-how to develop innovative technologies such as his EDM harmonic drive motor generator.
Well, the research initially that went into this arose from university education in the field power area, motor technology, in the electrical engineering department of Queen's University, where I was subjected to the topic of linear induction motors. And this arose my curiosity, which I started to look into at that time. Later, when I went to Short Brothers in Harland as Assistant Chief Project Designer, I tried to initiate the linear induction motor in various drives. I was given the task of designing a high-speed rocket launcher to shoot down Mach 1 plus aircraft, and this turned out to be quite an innovative project, which also incorporated not only high-efficiency induction motors, but also linear induction motors, driving the platform, the rotational platform. It had plastic ball bearings because of the low load and all the rest of it. Anyway, at a later date, I came across the problem that although these linear induction motors could produce high torque, continuous torque, that in fact there was a vertical force of 10 times the torque force that could not be used because it balanced out. It was the magnetic attraction between the stator coils and the back iron, but because of the balance in a normal induction or a normal motor, it could not be used. And this sort of piqued my curiosity again, and was a subject of curiosity for a number of years until I went to the University of Guelph, where we built one of these linear induction motor platforms, and again it was reasonably successful, but we couldn't make use of the vertical force. So until it occurred to me that maybe the combination of harmonic drive gearing systems could be used to take advantage of this. And this is where the whole initiation of the harmonic drive motor and generator occurred. The companies that have been traditionally in this area, obviously harmonic drive, which was invented by Musser in the 1950s, have been extensively used now, where you require lighter weight, robustness, small volume, extremely high reduction ratios for the low speed, high torque area. And likewise, so that's become quite interest because of the the very strong sort of simplicity of a harmonic gear, which has now been proven over, I guess, something like 50 years. And the other technology is the one that is involved in reluctance motors, which for a long time was not taken advantage of, simply because the software, the hardware, solid-state devices for control weren't available, which they are now. And now it has a renewed interest amongst people, particularly people who are looking for low-cost ruggedness, environmental suitability for higher temperatures, etc. So these two technologies, both of which, for instance, a company called Switch Reluctance Drives in England, which concentrated solely on switch reluctance motors, and then sold out to Emerson, I think. But both of these technologies were of current interest to many people, and a continuing interest in the drive for lower cost, higher torque in the low speed area. So we have these two companies at least, but many others. In other words, Harmonic Drive Technologies, which are two Japanese companies which have subsidiaries all over the world, and also there are switch reluctance people who are obviously engaged in through Emerson Motors. So, but neither of these companies have married the two technologies together, which seems to be an opportunity for the rest of us because of the simplicity and reliability. The first curiosity item of interest was how do you marry these things together? And when I saw that, for instance, there was this radial vertical attractive force, which is 10 to 20 times the normal torque force, how could I use that? And the opportunity to use it in harmonic gear became available then. That's what sparked the interest and the curiosity. And we went through many stages of development and experimentation. The venture capitalists provided the money. Unfortunately, they lost most of their money in the Nasdaq crash, but they provided the money to explore the technology in terms of what were these forces like. And of course, then I recognized that probably the switch reluctance motor and the attraction between a magnetic field and a back iron was probably superior to anything that else was available and had not been taken care of or had not been exploited, which is what I've tried to do, and I think I've done that successfully. What I did do was, in order to carry out some of the experimentation on this, I had the help of a consultant in the States who was previously the Vice President Research and Development of one of the large motor companies that dealt in servo controls and all the rest of it. And he had set up a business in the States consulting, doing computer simulation of flux flow in magnetic circuits, etc. And after about 6 volumes of simulation and whatnot, we came out with the current sort of windings that we've looked at. One we call them a punctual winding, and the other one which is a simple switch reluctance winding. The one that's in the experimental prototype is a switch reluctance winding, but it is more complicated than the simpler one, which should be less expensive, more rugged and all the rest of it, and much more easy to manufacture. It's just got coils which are slipped over salient poles, very simple, can be wound from outside, and this should give a better performance at lower cost than the other winding, which seeks to enforce the eccentricity of the harmonic gear flexus spline. So the technology was developed, and the basis was developed from a knowledge base that was already pretty well existing, but had not been married together. Well, if we start looking at higher torque and power density, you would realize right away that the harmonic gearing system, the principles which are embedded in my motor and generator, lead to very significant gear ratios. When we talk about a harmonic gear, we're talking about gear reductions in the order of anywhere from 300 to 1 to 30 to 1 in the standard harmonic gear catalog, which has been well proven and used. So that gives it an extremely high torque already capability. One could say, well, you could add a harmonic gear system to an electric motor, but that's additional parts, additional cost, and reduced reliability. So you do get the extremely high torque from the harmonic gear, but there is the additional contribution of the 20 times vertical force, which has not been used previously in motors. I mentioned before that this vertical force between the stator coils and the back iron was something in the order of 10, 20 times the horizontal torque force, which is not used in in any motor actually. But we have access to that. So that's on top of the 20 times the 300 times. So you can obviously see that there's room in there somewhere for extremely high torque and power density. And it's a very simple motor capable of cooling, so the only issue is extracting the cooling from it. Arranging for it would have to be liquid cooling if you're going to generate or take advantage of the full power density and torque density. Well, as I say, it's a technology that has been is available for adaptation to various platforms. Now, it's obvious if you look at the motor, experimental motor, which is not representative of the final version, that, for instance, that it has got no shroud. The actual shroud itself is the flexus spline. It is also replacing a geared down system. So you can take the weight of the gearing system away from my system. So it's significantly lower than equivalence, just in terms of weight and volume. If you look at the SMMA presentation in Chicago, and there's a sheet there from Gear Design, I think it's Gearden or something like that, where he looks at weights, volumes, speeds, torque, and all the rest of it. And they're all very significantly higher, the power and torque density than equivalents. That's significantly, not just 1 or 2 times, but somewhere 10 and whatever times. So these things all have to be exploited still in the industry. The need is there, but the solution is not obvious to most people. In this technology, you completely remove a rotating element. Motors all have a traditional rotor secondary, and in my technology, this is replaced by a stationary flexus spline, which has got a movement of probably only something of the order of 32 thousandths of an inch. So non-rotating is lower inertia, and not subject to failure, because the failures in harmonic gears relate to the failure of the bearings, the ball bearings, and the eccentric cam, which has to rotate at high speed, and that's the major mode of failure. Because as you go up in size of the main bearing for the elliptical cam, the speed of the balls increases to the point where it starts to fail, because it's just too high for normal ball bearings or even solid bearings. So you do not have a traditional rotor. You do not have any rotor, as a matter of fact, just an output gear, and this should be reduced to less parts count and higher reliability and less expensive manufacture and so on. this is where the stator windings are placed. I mean, they're placed in the center of the non-rotating flexus spline in the space normally occupied by a traditional rotor. So right away you've got a space and weight saving right there. The other question that comes up quite frequently in this sort of areas of technology is the switch reluctance motors tends to be noisy. But that applies to a traditional switch reluctance motor, and the noise comes mainly from the stator poles on the stator, which tend to bend with the torque, and that generates the noise. But in my particular case, I have eliminated that, and you do not have any salient poles on the rotor. You don't have any rotor either, and just the stator coils themselves. So that, and it's a sliding action in and out rather than a rotary torque motion. So that tends to get rid of the traditional noise that switch reluctance motors have. Well, it must be obvious that if you've got no rotor, then you've got no rotor inertia to take care of, which is very important in servo systems. Normally the rotor would be quite heavy and quite high inertia. I don't have that. In fact, it doesn't rotate, the rotor that I use. So you've eliminated that, and you've eliminated the associated inertia, which, as I say, is very important for servo systems and their acceleration. So you've got rid of that, and that's a big advantage. And the other one is the windage. When you're rotating a rotor, you have frictional losses which are due to windage, just its drag on the rotor. So you've gotten rid of that as well. So those are two advantages, and reduction of losses, increase in efficiency. Well, this we did extensive computer simulations of the flux flow and the losses, etc. And when you use the unipolar DC pulse excitation as opposed to, say, polyphase AC, you do not have any flux reversal. If you do not have any flux reversal, then you get rid of the hysteresis losses, and you get rid of a lot of the iron losses. So that is an important feature of this EDM technology. Yeah. Well, I am not aware of any system that allows you concurrent control of all three, torque, speed, and position. The torque is a matter of the current. The speed is a question of pulse frequency, and position is a question of pulse count. So you have independent control of all these three elements, which I don't believe any other system allows you the individual control of all three elements. And that's important in terms of servo systems, etc. Yeah. The subject of noise, if we read through Christian switch reluctance motors, the major source of noise is the bending of the salient poles